Hey, welcome back, my friends. This is to the series of ray optics, and this is part two of the series. As I promised, I'm going to publish regular videos at least every week. So this is like fourth day from my previous posting, and I'm back here. Let us get started. The agenda today is to do ray diagrams and the mirror formula. So we are going to complete reflections of spherical mirrors this time, and in the upcoming videos, we are going to start refraction of light. So welcome back again, and I'm going to revise a little for the students who missed part one, but I strongly recommend that you go back and watch part one, and then you are going to understand more of part two. Also, a very humble request, please subscribe to the channel, press on the bell icon so that you get notified every time I publish videos, and this is going to be a regular series from now onwards. So let's very briefly review what is ray optics versus wave optics, and we studied this in the previous video. So ray optics, we are dealing with the rays of light. We are not interested in whether the light behaves as a wave or a photon or a bundle of photon. I mean, we are just interested in how it is traveling in a straight line and then gets reflected off the mirror or refracted when it changes the direction. So we are interested more in the path of the light rather than whether it is a wave or a photon. But there are certain phenomena like diffraction, interference, scattering, polarization that will demand that we study the light as waves. And we are going to do that after we are done with this series of ray optics, which is going to be for next 3 or 4 videos. We will be done with ray optics, and then we are going to start with wave optics. So if you have seen the part one, well and good, but I can just give you 2 minutes here and revise very quickly what we studied in part one. Spherical mirrors, we started by saying let's take a glass sphere, cut a part of it like this over here, and then paint it on one side. So when you paint it on one side, you stand on the other side and you can see your image. So if you paint it on this side and you stand here, that became a concave mirror. But if you paint it here and stand and look at your face, it's a convex mirror. So you should be familiar with these. I'm not going to spend too much of time. My main focus in today's video is ray diagrams and the mirror formula. So please do revisit. So concave and convex, this is what we covered already. And we said it being a part of a sphere, it should have a center of curvature. Obviously, sphere has a center. And then this is what we call the pole. And then this is the center, the middle point between P and C is called the focal point. Watch the first video to see why it is approximately at the center of it. So focal point is the point where the parallel rays of light which are close to the principal axis are meeting, and these rays are called the paraxial rays. So in short, paraxial rays all will meet at the focal point. This is approximately located between the center of curvature and the pole. Same goes here with the convex mirror. So we are going to do ray diagrams, lot of them today. So there were three special rays that we covered. So this is focal point. We already covered that. There were three special rays that we covered, and we said, okay, the laws of reflection are always valid. You can always drop a perpendicular to the point of incidence, measure the angle of incidence, draw the angle of reflection, and you are going to get the path of the ray of the light after reflection. But we said, okay, there are three special rays where I do not need any kind of measurements. So number one ray was, and I gave you the reasons for that in part one video, so watch that. So the number one ray was if a ray of light is going parallel to the principal axis and obviously close to the principal axis, as in ray number one here, it is going to reflect back and go through the focal point. So no measurements needed, parallel ray goes to the focal point. Second special ray was this, a ray of light that goes through the focal point after reflection will go back parallel to the principal axis. So exactly opposite there. And that goes well with the reversibility of light, principle of reversibility of light. The third special ray was when a ray of light is passing through the center of curvature after hitting the mirror, it is going to retrace its own path. It is not going to change its direction. It just goes in and then comes back. So these are the three special rays I am going to use today. So let us get started. Let's try that out. So this is a summary. We already covered that. You can take a screenshot. You can pause the video here. Try to understand this. If you have understood these three rays of light, you have understood the ray diagrams. Nothing to memorize here, just pure understanding. No exam being targeted right now. We are trying to learn physics. We are trying to learn the concepts here. So let's try that out. So let's try that out. So let's make our hands dirty and start doing the ray diagrams. So let us say there's a, and obviously when you make these using your compass and protectors and scale and all that, you're going to do much better job than what I'm doing. But I'm trying my best with freehand tool. So bear with me, please. So, or maybe I can use a straight line tool at least here. So that's a straight line and that's the principal axis. Now let's mark a few points here. Let's call this point P as it is called. And let's call this point as the C, which is actually the center of curvature. And let's say this is the focal point, right? Now the goal of the ray diagrams is to find where the object, where the image is formed. So let's place the object somewhere, make a few rays, and find where the image is formed. And as I said, in the case of plane mirror, it's straightforward. Object is as far behind the mirror, image is as far behind the mirror as the object is in front of it. Also, the size is exactly same. It is upright, same size, everything the same, except your left hand becomes right hand becomes left hand and all that. Lateral inversion happens, except that nothing changes. But when you have these curved surfaces, the image can be bigger than the object, smaller than the object, same size as the object. It can be real image, it can be virtual image, it can be upright, it can be inverted. It completely depends where you put the object. So let's start with one example here. Let us say this green color is my object. It's an arrow here. So maybe a pencil that I put there, and I want to know where the image is formed. So now obviously part of it I already covered in the first video also. So there is sunlight or bulb light that is falling on this, and the tip of this pencil is reflecting the light of that, right? And that is how the rays of light get reflected. So light is falling on this, it's getting reflected, part of it is coming in into my eyes, and my eyes can see this. So my eyes can see this because the light is reflected of this, right? Now from those rays of light, there are zillions and zillions of rays of light, and obviously many of them are falling on the mirror. Many of them, infinite many, right? So many of them. But I will choose two of my special rays. So let's get started with one ray. Let's say there is a ray of light that is going parallel to the principal axis. What happens? We know that it's a special ray. It comes back through the focal point. So this is how it is reflected. And mind you, the color of this ray has nothing to do with the color of the light. This is just for explanation. Now let's take another special ray. Let's make it blue. And this ray of light goes through the focal point. What happens? If it is going through the focal point, it got to come back parallel to the principal axis. And that's what it does. So look at this. And as I said, you're going to do much better job than what I'm doing here, because I am trying freehand on the whiteboard here, right? So now look at these two rays of light, ray number 1 and ray number 2. So these rays of light actually, this was ray number 1. So let's look at these two rays of light. They meet at this point. This is the point where they meet. So if this was your tip of the pen, let's call it A. The image of A is formed at A prime here, A dash here. So this dot is the image of the tip of the arrow, and the baseline remains on the principal axis. So basically this is your image, the image of this arrow. So let's describe the image. Image is smaller in size, it is inverted, it is between focal point and the center of curvature. Nothing to be memorized. After you draw a couple of ray diagrams, you will see what happens. Plus I'm going to show you the pattern. So let's say the object was here and the image is formed here. What happens as I move the object closer to the mirror? So the pattern is, look at the pattern. As I move this object closer to the mirror, image starts going further away. It starts going the other way. And as it starts going the other way, it gets bigger and bigger. So look at the pattern here. I will draw this on the next slide so that you can see the pattern, and I'll show you some more ray diagrams maybe. But let's look at the pattern, because once you know the pattern, things are super duper easy. So the pattern is this. So let's say there is this is the focal point. This is the center of curvature. Let me put an object here. Image is somewhere between here, right? So let's bring the object closer. Same object, same size. Image will become bigger and become far away. So as I bring it closer, image starts getting bigger and bigger and far, far away. Right. So as I'm moving this object in this direction, image starts getting further away and gets bigger and bigger. Now at the point when I put the object here at the center of curvature, image is exactly the same size and right below that. So exactly below that, the same size. Now if I bring it any closer, the image goes further away and becomes bigger than the object. So far the object image was smaller than the object. Now it has become equal to the object, and then now it gets bigger and bigger. So now let's say I move the object here, image becomes bigger now. Look at this. And it keeps becoming bigger and bigger. And as you put it on the focal point, it gets so far away and so big. We call it, it's an infinite distance away. Infinite does not mean a zillion light years away, it's very far away, and it's huge. So as the object gets to the focal point, the image is huge. So that's the pattern. What happens when you bring it closer than that? Let's say you put the object here. This is where you get a virtual image, my friends. This is the virtual image, and it's bigger. So look at the pattern one more time. So one last time. So as the object comes closer to the mirror, image gets further and further away, gets bigger and bigger. So when the object was here, image was here. So let's see that. So when the object is here, the image is here. When the object comes to the center of curvature, image is right below that, same size. And all these are real images. The rays of light are really meeting at these points, right? Now as the object comes closer, image gets bigger and bigger, huge, 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 huge. And then at the point when you put it at the focal point, it's very large at very far away. But now let's say you put the object between the focal point and the pole. This is where you get a virtual image, and I will show you the ray diagram for this. And it's bigger. But I will also show you for comparison, because you have to do this as your home assignments, because in everything cannot be covered in these videos. Unless you make your hands dirty, you try these out yourself, you're not going to be able to understand this. Get like get the pattern here, try to understand the procedure or what the concept is, and then do it yourself. Take a pencil and a paper, no book in front of you, no book, koi kitab nahi rakhni, no book, just try to make them yourself. So in the case of a convex mirror, you will see, and I'll show you the diagram also if time permits, when you put the object here, image will always be virtual, but it is a small image. So see the difference between the virtual images made by concave and convex. Concave will make a big image, which is virtual, but then convex will make the virtual image which is smaller than the object, right? So big image, small image, that's the difference. So let's make another ray diagram, and let's get some practice here. And as I said, you got to try it yourself. If I do all of it here, there is no fun and there is no learning. You got to try it yourself. I'll do one more of this. So let's say this is the mirror's focal point, and this is my center of curvature. This is pole, and let's put the object here this time. Let's see how a virtual image is formed. So let's take one of the special rays. The special ray is parallel to the principal axis. It goes through the focal point. I mean, I could have taken other special rays like going through the center of curvature and all that. That's going to confuse you. Rather, what I will do is I will take a ray of light like this. Take it's incident here. So first thing I have to do is drop a normal at this point. But you know how to drop a normal because we covered that in video number 1. So from this point, you join this point to the center of curvature. But look at it. That itself is the principal axis. So principal axis is the normal at this point. So you measure this angle of incidence. You draw equal angle on the other side. As I said, you will do much better job than what I'm doing here. So these two angles are equal, incidence and reflection. So this was ray number 2, this is ray number 1. Where is the image formed? Wherever they meet, but they never meet because they're diverging now. So no problem, you can make them meet virtually. Virtually, as in trace them back. Okay, so this is the image form. It's huge image compared to closer it is, the bigger the image will be. So this is how you draw the ray diagrams. So for virtual image, real image, see the pattern yourself, try to make these, try to put the object somewhere here maybe, and see how the image will be formed here. Try that out. Try for concave, convex, and everything. So I'm going to move on to the mirror formula now. This is something as a home assignment. Try it out. Put it in the comments box down below that you tried it and did you succeed, or if you want I can make another video for you. But try that out and put your comments in the comment box below. Convex mirror will make an image like this. So again, it's something you try yourself. Yeah. So let's go through some of the uses of mirrors. Where do we use these mirrors? And these are just examples. You can come up with your own situations around you every day. So this is a kind of like you want to focus it. It's more like a solar cooker here. So this is the focal point. All the rays of light that are parallel here from the sun. Sun is far away, and we covered how the wave front gets flatter and flatter, and the rays become parallel as the object is far away. So these are parallel rays of light. They will all focus at the focal point. Yes, that's good, but then that is useful because so much of radiation is falling on this mirror. That's all concentrated in the small area, which will get a lot of energy, and you can use it. Now another use here is the dentist mirror for the concave mirror, right? Everybody understands this is concave mirror. Why is it concave mirror? Because remember, in the concave mirror, when the virtual image is formed, it's big image, and the dentist wants to see a bigger image of the tooth so that the problem can be identified. Now think about which kind of mirror this is in the car. Think about it. Pause the video. Think yourself. तभी सीखोगे. Me telling you will not help you unless you think yourself, analyze things yourself. So what kind of mirror is that? This is pure simple question for you. Very, very simple question. What kind of mirror is that? Hoping that you've already tried that. This is convex mirror. Because remember, in the convex mirror, image is small. If the image is small, many things can be covered. So when you have a rear view mirror here, you want to see lot of it because you want to cover all of the road behind you. So cars will be shown smaller, trees will be shown smaller, but you can cover a wide area in that. So this is going to be a convex mirror. If you have not understood, pause the video, think yourself. And the more you think yourself, more you analyze yourself, more the learning happens. Physics cannot be learned from the books. Physics has to be learned from your own observation, your analysis, from your day-to-day surroundings. Physics is not learned in the books. Books will guide you, they will not teach you. I will guide you, I will not teach you. You learn yourself. So let's move on. Um, and do a kind of very small question here. Where should an object be placed in front of a concave mirror to form a smaller image on the screen? I request everybody to pause the YouTube video right here, think, analyze. Maybe if you have enough time, make a ray diagram also, and then return back. Okay, so hoping you've already done that, pause the video, try it out, let's see. So I have a concave mirror, so let's make a concave mirror. I want to make a smaller image on the screen. No problem. Smaller image on the screen, matlab real image. Real image के लिए small. If I put my object here, I know it's a big image. No, नहीं चलेगा, नहीं चलेगा. If I put it here, it's the same size, नहीं चलेगा, है ना? So to form a smaller image on the screen, you got to put your object beyond C, and then you will have an image here. Obviously this is a real image, so you can put your palm here, some screen here, something here, and you get it. So the answer for this will be beyond C. Now what about large image? Large image we already know. If we put an object here, the image will be large beyond C. You know? So large image on the screen is going to be between F and C. So you put your object between F and C, you get a large image on the screen. If there's a large image which is virtual, then you put it here, right? Because then that's a virtual image, but we want it on the screen between C and F. Chalo, let's move on then. We'll do some mathematics now. So sign convention is nothing new. You have already done that in your junior grades, 7th, 8th grade, whatever. So you have done Cartesian coordinates, right? So remember, you have already done this in your math classes. You make this as x-axis, you make this as y-axis, and then you write +1 here, +2 here, -1 here on the other side. So this is all -1, -2. Same goes for +1 on this side, +2 on this side, -1, -2, right? So you've already done this. So anything going rightwards is positive, leftwards is negative, upward is positive, downward is negative. That is all. That is the sign convention, with a few more things. So what we are studying here is sign conventions when we are dealing with mirrors and also lenses. So we'll start refraction in our next video. We will start studying lenses. The same sign conventions apply. And what are conventions? I have covered that earlier also in a few videos. So there are two things. One is laws and there are conventions. Laws you cannot break. The laws of the nature. Things will fall down. Those are the laws of the nature. Convention is something we have decided. We have decided to call this x-axis. We have decided to call this y-axis. Nahi pasand aata, you change it. You can always break the convention. You call this as p-axis, you call this as q-axis. Or why that? You can call this as x-axis and call this as y-axis. All your analysis will be correct, but people will get confused. If you do not follow conventions, you're confusing others, right? That's the only thing. Otherwise, you can break the conventions, no problem, solutions will be right. You don't want to confuse others, right? So sign convention here is object is always placed on the left hand side of the mirror. I covered this in video number 1 also. So always put the mirror like this, stand here to watch your face. You never ever do this. You never do that. This is your mirror like this and then you're standing here. Right? Obviously your solutions will be right, but you're breaking conventions, confusing everybody. So convention is object is always placed on the left hand side, and the other thing is this pole is your origin. Think about pole as the origin. In case of lenses also we'll see that. So if pole is origin, and if you're measuring on this side, this is positive distance. This is negative distance. This is positive distance. This is negative distance. Ho gaya. That's all the sign convention is. Now let's make a practice of it. So let's see concave mirror. Concave mirror ये होता है. Concave mirror is this. Now obviously this is the origin. Now think about the focal length. Focal length. By f to इधर है. So you got to measure in this direction. So focal length is negative here, my friends. You don't have to memorize. Understand the concept here. So now look at convex. Convex here. Convex here. So now this is the pole and this is the focal point. So focal length is in this direction. Focal length is positive. So focal length will be positive for convex mirror. It is going to be negative for the concave mirror. Simple. Now there are few symbols also that you have to understand, and these are different in different books. You will see different conventions. So some of the books will use U for object distance. Object distance. And I don't like it because that confuses many students, but many of the books will use U. I would rather say DO as in distance of object, but that's fine. Let's actually use those better conventions. I don't really like UV because see that confuses. So let's call DO as the object distance. Now because we are placing the object always on the left side of the mirror, this is always negative. So there is nothing to explain in this, right? Object is always placed on the left hand side, so it is always negative. Now what about distance of image? Distance of image, okay, there is distance of image as in how far is the image from the pole. If it is a real image, it's made on the left hand side, so the distance of image is negative. Again, don't try to make this table and memorize, but understand it. And then it is going to be positive for virtual image because virtual image is formed on the behind the other side, right? So positive for virtual image. How about the focal point? Focal length is going to be negative for concave. And I'll do couple of questions for you today, and then you can see this working. And positive for convex. For convex, it is going to be positive, as we already saw here. Now there are two more variables. One is the height of the object. So height of object, as a convention, you always put object upright. सीधा रखना है, उसको उल्टा नहीं रखना. So object is always put upright. So height of object is always going to be positive. So that's by convention. There are certain exceptions to that, but in general. Now height of image when it is real, it is inverted, right? So inverted image mein height of image will be negative for inverted, and height of image will be positive for upright images, as in real images. ठीक है ना? So इसमें there is nothing new. This is all x-axis, y-axis. So let's do a question, and that will make things easy. So mathematics. Sorry. So before we do that, we should also cover a two formula here. So how are these things related? So the relation is 1 over f is equal to 1 over distance of image plus 1 over distance of object. And all these derivations are super duper easy. You can take any book and you will get it in 2 minutes. This is called a mirror formula. Similarly, we'll have a lens formula that we'll cover later on. Another thing is magnification. The definition of magnification is, it is how big is the image, matlab how much is the image magnified, right, compared to the height of the object. So if height of the image is double, the magnification is double. If the height of the image is 1/5, the magnification is 1/5. You still use the word magnification even when the height of the image is small compared to object. Let's call it magnification. So magnification will be a fraction in that case, as in 1/2, 1/3, 1/20, whatever, right? So height of the image divided by height of the object, that's the definition of magnification. But turns out as in when you do some analysis with those, and it's all mathematics, that's not even physics, you can do that, it's very easy. That turns out to be equal to negative of distance of image by distance of object. So this is the definition, but mathematically that also turns out to be this. And we'll do some questions, and we'll see how we can use this. So let's start. So here is a tiny question. All you need is these two formulae here. Please go through this, note it down, pause the video, try this yourself. It might take 1 minute, 2 minutes, 10 minutes, whatever it takes, and then return back. And put it in the comments box. Did you find this useful? Were you able to learn the mirror formula with this or not? Because in the next upcoming videos, I can prepare better questions then, right? So everything in physics, any problem that you get, I always start with making some pictures. So let's make pictures here. So there's a lens, लिख दिया गलती से. So this is actually a mirror. My mistake. I'm really sorry for that. See, I type these questions myself. These questions are not from any book, and when I type them, I have n number of things going on in my brain. So sometimes I type it wrong. I'm really sorry for this. So it's a concave mirror of focal length 20. So I know this is the focal length, and this was the origin, and this is where negative 20 by focal point. Now, obviously, there's center of curvature, which is at negative 40. Now, object is placed at 60 centimeters from the mirror. So obviously, the reason for making these images is to also get visual, like where is the object? Should the image be bigger or smaller or whatever? So now again, pause the video, think about object is placed beyond C. What kind of image are you expecting here? So for me, I'm thinking the image has to be somewhere here smaller, right? Because that's what we already saw. So this is my expectation, and let's see if the expectation from the mathematics are exactly same. So image should be real, inverted, upside down, and between C and F. That's my expectation. Okay, so let's do mathematically. Ignore this now. This is for a cross check here. So this is how you self-check if your analysis was right. So let's go purely mathematics. So what is the data given to me? The data given to me is the focal length is given. It's a concave and the focal length is -20. What else is given? Distance of object. Distance of object by convention is negative. So distance of object is given to me as -60. And obviously it's always a good idea, even if it is positive, to put a plus sign there so that you know you have considered the plus and the minus. You have to find the distance of the image. है ना? So let's use the mirror formula. 1 over f is equal to 1 over di plus 1 over do. Simple, that's it. Just plug in the values. So negative 1 over 20 is equal to di, so I do not even know. I have to find that. And I think there is some problem with the whiteboard today. It's freezing a little. So I'm really sorry if you're finding this video frozen at times. I will check it, but for now I don't want to disturb this video, so I'm continuing. So 1 over 60 and a negative. Now this is mathematics. You take it on the other side. So this becomes 1 over 60 positive and a minus 1 over 20 is equal to 1 over di. So solve this, di gets negative 30 centimeters. That is exactly what I was expecting. It has to be between F and C. Not exactly at the midpoint, but I got it at midpoint. But somewhere bit more than 20, less than 40, I was expecting, I am getting. हो गया ये तो है ना? This part is verified, cross-checked. Height of the image. How do we find the height of the image? So let's use another formula. I know magnification is equal to height of image by height of object, but that also is equal to negative di by do. First, I'll move my own image here. So now height of image has to be found. I do not know height of image, but height of object. It's 4 centimeters big, and it has to be positive 4 because 4 centimeters, and it's upright. Object is always upright. Minus sign because the formula demands it, but then there is another negative sign because value of di itself is negative. So be careful when you're putting these values. Signs have to be there. Do is also negative, that is negative 60. So when you simplify, the height of the image comes out to be negative 2 centimeters, while the height of the object was positive 4 centimeters. So now look at it. My expectation was that the image has to be smaller. Small ही तो है. My expectation was image has to be inverted. It is inverted because it's negative 2. So perfect. Everything is matching here. So height of the image is negative 2 centimeter. Nature of the image, it is a real image. कैसे? How do I know? Because distance of image is also negative. Okay. So now let me tell you how you would find what the nature completely. First of all, I'm claiming that this is negative. This negative sign is telling me, and again a request, whatever I'm going to speak for next 1 minute, it's very important because books don't teach you this way. So look at the values I'm looking at. I'm looking at this negative sign, and this negative sign tells me the image is formed on this side. So this tells me this thing is telling me that the real image is real because of this negative sign. This negative sign tells me the image is inverted because height is negative. Now this number tells me that the image is smaller. You see what I'm trying to say? So look at these numbers and signs. You should be able to see everything, and then you can cross check with the image that you already formed. I'll give you one of the questions to try it out. Everything is similar except that this is a concave lens पे लिख दिया है ना. This is mirror. So concave mirror. Sorry, convex mirror. I wrote it as convex lens. It's a concave mirror. Lenses we have not done yet. So this is exactly same except that convex mirror. Convex mirror में the change will be focal length will be positive. So try this out. Write it in the comments box. So again, I'm saying do not do this question in 1 minute, 2 minutes. This is not a speed test. Take enough time, 5 minutes, 10 minutes. Try to analyze it. Make the image. See where you're expecting it. You're expecting convex, so it has to be on the other side. Virtual honi chahiye, smaller, erect, and it should not be inverted. So height of image when you find it has to be positive. So write down those expectations. and then use the formula and then match one to one expectation. Yes, match, match, match. If they are not matching, then there is some calculation mistake, some conceptual mistake. So this is your homework. Try this out. I know you can do that. So in upcoming videos, I'm going to start refraction. So next time, basically next time is not going to be long time. It may be next 3-4 days. I'm going to publish a video and I'm going to start the refraction of light. So again, request to you, spread out the word. This is not a money making kind of scheme here. I'm just trying to, because many students had contacted me to teach them, but my fee actually is a little high and many students are not able to afford it, and that's understandable. So some of the students said, sir, एक बार video बना के YouTube पे डाल दो, we all can see them and all that. So that's what I did. So 15 students actually, they regularly watch and they're benefiting from this regular videos. So make sure you spread out the word. As the community grows, more and more videos will come because I'll get more enthusiasm, more students are benefiting from this. So I'll see you in few days from now. So I always end the class by some nice quote. So do not wait for an opportunity. You got to create that. Create the opportunity. Okay. So thank you. Good luck. See you soon. Bye bye.